Good afternoon, everyone. Welcome to our November SLDS webinar. Our speaker today is Dr. Nate O'Connell from Wake Forest University. Nate is an assistant professor in the Department of Biostatistics and Data Science at the School of Medicine. He earned his PhD in biostatistics in 2018 from the Medical University of South Carolina. Dr. O'Connell is a collaborative biostatistician and data scientist. He has extensive research experience developing models for various types of data in the medical disciplines of cancer, pediatrics, neurology, emergency medicine, and EHR data analysis. Dr. O'Connell is an expert in design and analysis of clinical trial, particular dose-finding trials, longitudinal and cluster data analysis, mixed model, analysis of EHR data, analysis of continuously monitored patient data, Bayesian methods, missing data, and prediction modeling using traditional and machine learning methods. And today he's going to tell us about a comparison of methods of cross-validation for small data. Let's welcome Dr. O'Connell.
Thanks for having me. I'm excited to be here to share some of my work. This presentation should take about 55 minutes. I've given this talk I think twice before, and been 55 minutes to about an hour. So I'm excited to share with you my talk today. Thank you for that kind introduction. I'm Nate O'Connell. Like I was introduced, I'm an assistant professor in biostatistics and data science at the Wake Forest University School of Medicine. And the title of my talk today is A Comparison of Methods of Cross-Validation for Binary Classification with Small Data. I like to start this talk, and I know this audience is probably well suited to already understand this, and this is an intro that you all probably have read or heard before, but I like starting this talk with inference versus prediction. Traditional statistical inferences where we seek to uncover and understand relationships, and we have this little screen over here, relationships between variables in nature, and we quantify the uncertainty of those estimated relationships that we uncover. With estimates of variability and confidence intervals or credible intervals, if you're a Bayesian, interpretations of our finding typically come with uncertainty baked in. We run a model, we get our estimates of the associations, and we have estimates of standard errors, and we can calculate the confidence intervals or, again, credible intervals if you're a Bayesian. Sometimes we try to replicate findings and find something different. From a statistical, philosophical perspective, we can always fall back on random chance as valid reasoning. Well, this study did not replicate our results, but random chance. Maybe what we found was not true state of nature, and we just happened to have a false positive. But in prediction modeling, we seek to make develop models actionable through prospective predictions, and arguably the stakes are a little bit higher. Uncertainty still exists and can be quantified, but the consequences of acting on a poorly developed model due to random chance can be more severe. If we develop a model that's not well calibrated or not well performing when externally validated, then we might be the consequences it could have on patients and medical data could be severe. So inference gives us understanding through modeling, but predictus gives us actionable models. And clinical investigators with whom I work with are often interested in prediction. I'm a classically trained statistician in biostatistics, but more and more has my work gravitated towards the development of clinically actionable prediction models in prediction model development. And here's a few motivating problems. These are real examples that I've worked on and developed models for over the last from the last few years. For example, in the ED, given a patient's baseline measurements and characteristics within the first 24 hours after admission, can we predict patients with pulmonary embolism at high risk clinical deterioration? Clinical deterioration being a composite of all sorts of really bad things that could happen to that patient, including death. Or in a clinical trial, given a patient's baseline information, can we predict patients at high risk of dropping out of the study within 6 months? Or in patients with breast cancer on chemotherapy, can we predict patients at high risk of significant decline in left ventricular ejection fraction? Now, something that all of these studies had in common, fewer than 500 patients. Well, how much data do you actually need to develop a prediction model? Well, conventional wisdom or AI might suggest the more the merrier. You'll often see recommendations of you needing thousands or tens of thousands to develop a sound, reliable model. And obviously, the more the better, but we don't always have more. There's the old rule of thumb of 10 events per predictor, but that's far too vague. I mean, what about categorical predictors with multiple levels? Some recommendations are for more than 10 events per predictor, some less. But again, it's a very vague, understated kind of rule of thumb. It doesn't stand up to scrutiny. A paper that I really like that I've cited before and used before, I mean, tries to quantify this a little bit better and provides a sample size calculation for prediction model development, which has a great R calculator. And they're a little bit more optimistic on samples not needing to be so large, assuming a true ROC-AUC of 0.85 and an outcome class prevalence of 34% and 17 predictors. Where did I get those numbers? Those are averages from the simulations I'm going to show later on in this presentation. This approach calculates as 1 need to 390 to have a good prediction model. But, you know, sometimes we just don't have a choice. We have what we get. Clinical data can be expensive to collect, time-consuming to collect, burdensome to patients. Like scans take time. MRIs take quite a bit of time, and it's a pretty limited resource if MRI scans are, you know, the data you're trying to collect to predict on. Labs can be invasive. Questionnaires can take a lot of patient time. Various physical tests takes a lot of time. And sometimes it's just simply not available. Like with medical data, we just simply don't have access to large amounts of data. And if the diseases are rare, if we're trying to develop a model on rare disease, they just don't exist. So of course, more data would always be great, but more data is not always feasible. And it's just a fact. Like we have to accept that. We have what we have when it comes to certain types of data. So what exactly is small data? For the purposes of this talk, I'll define that. There's no really standard threshold that makes data small relative to quote unquote big data. According to Wikipedia, small data is data that is, quote, small enough for human comprehension. It is data in a volume and format that makes it accessible, informative, and actionable. I like that. It pretty well defines medical data that I work on often. So for the purposes of our work presented today, we'll consider small data to be data sets with less than or equal to 500 observations, regardless of the number of predictors or features one might be considering in the model. And again, why 500? Well, in the world of machine learning and prediction modeling, 500 generally wouldn't be considered big data or massive sample size. And anecdotally, based on my experience working with clinical investigators, type of data I work with, 500 generally is about the upper end of a reasonable sample size for a lot of the studies that I work on. So what are the issues with small data specific to developing prediction models on it? Well, it may not be comprehensive and reflective to the overall global data from which we wish to generalize to, and especially in cases with rare events or predictors. Rare levels of categorical predictor variables can be poorly represented. For examples, less prevalent categories of race, such as Pacific Islander or Native American, at least in the patient population that I work with, are often very poorly represented with these small sample sizes. Developing prognostic models for these patient populations of these races is very difficult. Potential for large variability in performance estimates due to the inherent randomness in the subsample available. We're all probably familiar with types of bias. So we have this existential question of, do our data and the models developed from it accurately reflect that of the true population we wish to generalize? Well, this is when I bring in my favorite statistics quote. Everybody has probably heard that all models are wrong, but some models are useful. And modeling with small data can be useful. Of course, more data would be better, but it's, like I said, it's not easily accessible at all times. We should be careful to make definitive claims when developing prediction models using quote unquote small data. And goals often should be explorative in nature, hypothesis generating, proof of concept. Often when I'm developing prediction models and I only have a sample of 100, 200 models, the goal is to see, like, is this feasible? Can I get decent enough prediction metrics to say, like, okay, I think we could build something here, but we need more data to get a better model, a more robust model that we're confident like putting out into the wild. And high variability does not mean not useful. Again, back to that point I just made. If I have a sample of 100, I'm not going to develop a model on that using cross-validation and then send that out into the wild to use in practice. But if I have that model and I estimate an AUC of 0.85 and confidence interval around that of 0.6 to 0.98, okay, that's a pretty large confidence interval, but again, it's high variability, but again, it's still pointing in the direction of maybe we can do something here. We just need more data. So high variability does not equal high, not useful. It's up to us to interpret what is useful. And I really like this quote I found in a paper published in 2018 that basically we should accept that small study sizes on prediction are exploratory in nature and best show potential of new biological insights and cannot be expected to provide clinically applicable test prediction models or classifiers. So keeping that in mind with small data, well, how do we know how to trust our data? I like this XKCD comic. I love XKCD. You could find one to fit pretty much any scenario. So I usually incorporate it in the talk. So I like this little comic here. But how can we trust our data? We just keep stirring it up until we find something that works, right? Well, we can train and test. Everybody here, I'm sure, is familiar with the concept of cross-validation. Very simplistically, we take our predictions and test how well they predict on our data we already have outcomes for and assess metrics such as the AUC the AUC for the receiver operator curve, area under the precision recall curve, or we can assess calibration using metrics of Breyer scores or looking at calibration plots. And generally speaking, AUC, wanting to see that between close to 1. Anything better than 0.5 means there's something there, but closer to 1 gets us close to perfect prediction. And we go through, but we have issues with testing and training, such as overfitting. Machine learning models, specifically random forests, which I work a lot with, can learn too well on the data they're trained on, which leads to overfitting, especially when we're testing on the data we use to train the model. Performance appears better if tested on data set used to train it. So then we could very, very easily, the very most naive approach or the simplest approach is go to split sampling. Well, we could split the data into training sets and test data sets, use 70% to train data and test it on 30% that wasn't used to train it. And a lot of researchers do this. And when you have massive amounts of data, hundreds of thousands or millions of observations, this is fine. Like you're not gaining anything by doing more. So it's valid. But with small data, there's a lot of variability in the random split that comes with that 70-30 split for the training and testing. And you're not using all the points available. And when data are scarce, you want to be using everything that you have. So that's the simplest form of validation and cross-validation, simplest form of like testing and validation. But to get better than that, we have other cross-validation techniques, which use some form of resampling on data to train and test a prediction over and over again in various ways. So the goal of these techniques is to estimate our error and performance of developed prediction model in terms of its generalizability. So what we hope is really two big things here. We hope for low bias in the estimate, so low bias in the AUC or precision recall or calibration, and then if you have a decision threshold you've already decided on, low bias and sensitivity and specificity and positive predictive value and all the other metrics we could look at, and low variance. What do I mean by low variance here? Well, low variability around what that estimated metric is. So we want the bias to be low and we want the variance to be low. So we're going to go over very briefly the common methods of cross-validation that I'm going to compare later on. So focusing on this work, split sampling, which I've already discussed, then we'll have repeated split sampling or Monte Carlo cross-validation, often referred to in the literature, and I will abbreviate this throughout the remainder of the talk as MCCV. There's k-fold cross-validation, leave one out cross-validation, which is a specific case of k-fold. There's repeated k-fold cross-validation, so we just repeat k-fold cross-validation however many times. And then for random forest specifically, the out-of-bag error estimates that we can use to estimate all of the prediction metrics we care about. And then there's additional methods not evaluated, including bootstrapping on adjusted 632, 632 plus bootstrap that I'm not looking at specifically here, largely because the bootstrapping is very similar to the already performed out-of-bag estimates performed in random forest, and much of my results are focused on random forests. Again, split sampling, the very most basic level of this. We have 100 data points. We'll take 70, develop a model, and predict on the other 30, and whatever the prediction metrics are on those 30, those are estimates of AUC or whatever it is. It's the simplest, most naive approach, and again, very good for really large data, but with small data, a lot of variability that can occur with these random splits. So, well, how do we get across that? Well, what if we just do it, 10, 20, 30, 100 times? So do random split, test, train, and repeat that 10, 15, 20 times, and then average over those random splits. And then you have Monte Carlo cross-validation. or repeated split sampling or shuffle split sampling. There's numerous names for it. I think intuitively, this is the, probably most, if you've never heard of cross validation before, never done this before, and you're a statistician, it's probably the next thing you think of or could come up with. Well, then we have k-fold cross validation, which we split the data set to have k number of data sets, and we have k different folds. And each time the subsample used to test on versus train on is mutually exclusive from the other iterations. We have repeated k-fold cross-validation, where we do k-fold, but then we repeat it n number of times. And then lastly, there's the out-of-bag estimates in random forest, which is the form of internal bootstrapping. And then ultimately, we can get performance metrics estimates using out-of-bag samples, out-of-bag errors from random forest models to estimate things like AUC that we care about. What does the literature say about cross-validation? Because I've given you all these, all of these methods that I'm sure most of you have heard of, but which should you use? A lot of people use split sampling when they shouldn't, and a lot of people use Monte Carlo cross-validation just because it seems intuitive to use it. K-fold is really popular, probably the most popular, but what should you use? If you go to the literature, go to Google Scholar and type in, what should I use for cross-validation, particularly like with small data, and why? And you'll get a lot of conflicting results in those conclusions or abstracts of these papers. Some will tell you that k-fold is biased, and some will tell you that it's not, the bias isn't that bad. You'll find the variance, I'm not reading up this, but I'm just going from memory, like you'll find bias variance trade-off with choosing your value of k for k-fold cross-validation. You'll see very little about out-of-bag estimates with random forest specifically compared to all these other forms of cross-validation, which is why I've thrown this in, and I'm interested in it. In 2022 paper down here stated that Monte Carlo cross-validation is most accurate than k-fold cross-validation with small data. That's interesting because other papers have said k-fold's better. So what should you use? Nobody knows. Well, I'm sure somebody knows, but it's convoluted. So there's a lot of gaps in the current knowledge. Most studies comparing methods of cross-validation are based on simulated data, just a few real data sets, or do not consider random forest as a classifier. And few compare Monte Carlo cross-validation with repeated k-fold, and also few look at out-of-bag error estimates with random forest specifically to all these other forms of cross-validation. With respect to these out-of-bag error estimates, you also have conflicting information. You have a paper in 2012 and 2015 saying out-of-bag estimates are reliable. 2016, out-of-bag estimates need to be further tested in various conditions. And from the Google developers on the Google's AI machine learning page, random forests do not require validation data sets, largely because they conclude that out-of-bag error estimates are suitable for making these estimates of your prediction metrics. So there's been a lack of benchmarking studies ultimately in the literature that directly compare out-of-bag prediction performance to other forms of cross-validation. I started thinking about this problem 5 years ago when I started developing prediction models for people, and I came from my doctoral work was in early phase clinical trials using Bayesian methods, and then I started developing these models and learning prediction modeling and the language of prediction modeling, and I was seeking, if I have small data, I just want to know like what form of cross-validation I should use, and I want empirical evidence as to why. A paper of my colleague, Jamie Spicer in my department, she published this in 2019, which has now garnered over, it just hit over 1,000 citations last year in the last 5 years. Just a very basic, what method of variable selection should you use for random forest? And this is the type of paper I like to use as an example that I was looking for. What form of cross-validation method should I use if I want to develop a prediction model? And there was just no clear, concise paper like this saying, I mean, it was just a lot of that conflicting information. So this is what I was looking for, but what I couldn't find. And there's that quote of be the change you want to see in the world. So I'm going to, write the paper that I want to see in the literature. So that's where we started with this, a benchmarking study to compare these methods of cross-validation. The questions we seek to answer are which method of cross-validation, specifically in random forest in this case, is optimal, or is there even an optimal approach? How do bias and variance of that bias compare between these methods of cross-validation? For k-fold, what value of k should we choose? And is repeated k-fold worth the computation time. It is computationally the most complex form of k-fold cross-validation. If you have fivefold or you want to run 10 times fivefold cross-validation, well, I mean, assuming a few things, like it's just 10 times longer to run that if you're running a single CPU core. So the underlying premise of this benchmarking study is, in practice, what if we could know the global population parameters regarding the predictive metrics we want to know? But in real life, like we don't know. Like we have small data, and we're extrapolating this to a broader global population, which we don't have access to. But like, what if we could know? So what we did, under this premise, we pulled all of the data sets from OpenML that met the following criteria, where they had greater than 10,000 observations, less than 50% missing data, more than 5 but less than 500 total predictors, and were a binary classification outcome. For data sets with multiple versions, we simply selected the most recent, which gave us a total of 47 different data sets that met these criteria. And the reasoning behind these parameters, well, for 10,000 observations was we reasoned that if there's more than 10,000 observations, that's going to be big enough for us to consider that a quote unquote global sample. So for each data set, we let each full data set of greater than 10,000 equal that global population. And then we'll draw a subsample of 100, 300, or 500 from that global population. And we'll develop a prediction model from that sample of small n, 100, 300, or 500. Based on that sample of 100 or 300 or 500, we will develop a model using some form of cross-validation to estimate ROC AUC, precision recall AUC, and Breyer scores. And then we will then take the fitted model, train on that subsample, and then use it to predict over the global sample that we originally drew from and know the outcomes for. So we obtain the true performance based on the global data. So this is simulating if we had the global data and could test our model in every single possible observation in the world, what is the actual true performance of our model that was trained on just the subset? So we can obtain that. And then we calculate the bias of what did we estimate with the cross-validated sample from the small data set versus what was it truly when we applied it to the full knowable data set. And then we repeat this 50 times for each data set and sample size of 100, 300, or 500. And then we'll report the mean estimates of each of the metrics, ROC, AUC, PR, AUC, and Breyer scores, the median, the variance, the 95% coverage of the bias, and the IQR across all these replications. In this benchmarking study, all this was coded in R using tidy models in the package Ranger as the engine for random forest and GeoMNAT logistic regression models. We've also started running results on these using neural nets. As well. I don't have those in this paper, and most of this is going to be focused on random forest, but the first few sets of results will also include some lasso logistic. For missing data, if missing data was present, we simply used mean or mode imputation. Assessing bias due to imputation methods was not part of this, so we just needed to fill them in. Default parameters were assumed for all the models. So the default parameters for Ranger is the number of trees, the number of tries per split, all of that. That's all what Ranger uses at default. And if you really want to scrutinize my code and go over this or run these yourselves, you're more than welcome to. This is all available on my GitHub page found here at Nate O'Connell, PhD /small/data/CV. So that's all there. So we'll get into some results. First, we're going to compare ROC AUC by these cross-validation methods and sample sizes aggregated across the replications and data sets. So for each box, like each individual box, you find, is it in the 100, 300, or 500 row effectively? And this box represents all of the possible results for bias estimates across all the replications across every data set. The boxes themselves, like the little IQR box, is the IQR that represents the 50% coverage. And these whiskers I've programmed to represent 95% coverage. So what you'll see here is effectively 95% of what the estimated biases were for each method at each sample size for each type of cross-validation metric found on the left side of this plot. So what we see here is, I mean, most are reasonably unbiased. The black line in each box is the median, the red dot is the mean. So we see that the median is pretty much unbiased for every single method. So that's good to see. But we see split sampling, repeated split sampling out of bag error estimates in terms of mean estimates are a little negatively biased, which gets less and less as sample goes from 100 to 300 to 500, but you're about 2-3% off in terms of mean bias for the sample sizes of only 100. K-fold cross-validation a little better. Tenfold is better than fivefold. Repeated tenfold cross-validation 10 times is equal in mean and median bias to that of just plain tenfold cross-validation. But if you look at the box, the IQR box, it shrinks just a little bit. So you do increase a little bit, or you do improve the variance around it a little bit by repeating K-fold cross-validation, but very marginally. So my results from this slide, I have a bunch of slides that look like this. My results from this slide is that K-fold looks generally best. Most are relatively unbiased, but K-fold's looking to be least unbiased, with the spread of the variance being about the same for everything except for split sampling has a larger IQR and a larger 95% coverage than any other method. So that kind of confirms what we probably already all intuitively think of is don't use split sampling with small data. But for the rest of the methods, it really didn't matter all that much. These are the same results minus the out-of-bag samples because we don't have those for logistic regression models. And this just simply compares the same cross-validation methods, but ran using lasso logistic regression, where we see the spread of the data, the IQRs are about the same for every method except split sampling, which is a bit larger. K-fold is a little bit less biased than split sampling and Monte Carlo cross-validation, and tenfold is a little bit better than fivefold, but not hugely so. What about precision recall? All right, well, this flips the script a little bit with precision recall. K-fold is a little positively biased, whereas split sampling is a little negatively biased. Out of bag is kind of close there. It's a little negative, close to unbiased when you get the 500 sample size. But what we see here is opposite of what we saw with of ROC AUC. In the ROC AUC, we see that fivefold's a little less biased, or a little more biased negatively than tenfold. But here we'll find that tenfold is actually a little bit has a little bit greater of a bias, and this is a positive bias than fivefold cross-validation. The spread of the data, if we look at this 95% coverage in the IQRs, are about the same. I didn't see major differences here, but in terms of biases, we're seeing that decrease in the folds is helping a little bit. Yes. I see a question.
There are a couple questions in the Q&A. One
Sure.
is, was the original distribution of T?
Where are you? Hold on. Let me look. Where's the? Let me pull up the question so I can actually see them.
Thanks.
Webinar chat. How? I can't see all the original questions. No.
No problem. I can read it to you. So the first one is, what was the original distribution of T?
Of T?
Uh-huh.
What?
Oh, sorry, TG.
TG? Oh, hold on. What TG? I'm misunderstanding this.
Let me see. Could you let me talk to the audience. Is it possible to elaborate this a little bit? Yeah. So let me see. Did the original or global distribution affect the outcome of bias and variance of the foods?
Okay, so we will get into that. So I will show results after this that are looking at the imbalance of the actual outcome. So we're getting into, these are all binary classifications. So we'll look at imbalance of the outcome distribution, and we'll look at a subsample of that.
And another question is split sample same as holdout cross-validation? Yes.
I think for these purposes, yes.
Okay.
Okay, so yeah, so all right, where am I at? So I go to the next slide. So I just covered this. All right, so lasso logistic, we see largely the same kind of conclusions here as random forest. So I'm not going to spend much time on this slide. And for these reasons, these are the only time I'm showing the lasso models because they largely are the same as what we see with random forest for the most part. And lastly, looking at Breyer scores as my chosen metric for calibration to assess bias and variance of note that Monte Carlo cross-validation split sampling have actually pretty positive bias relative to the others, but everything's a little positively biased, which in terms of Breyer scores would mean we're underestimating our calibration performance. Now, this could make good sense given that we are using random forest here, and we know with imbalanced data, we can have some issues with estimating with calibration, especially when the data are less balanced. The data outcome distribution is less balanced. So we will look at these results with quote unquote unbalanced data. So let me next slide. All right, here it is with lasso logistic regression. So we see that does the effect of lasso, the effect of imbalance or of Breyer scores when using lasso is a little bit lessened if you compare this 500 plot to this 500, a little bit less severe, likely due to the way lasso is fitting the models and estimating predicted probabilities versus random forest, which is going to be these are all the different data sets. So we have data sets ranging from 5% for the minority class up to 50% of the minority class. So those lower prevalent outcome classes data sets are probably pulling these Breyer scores up a little bit. But nevertheless, all things else equal, tenfold or k-fold cross-validation was estimating your calibration performance a bit better than a form of split sampling. So a quick summary of what I've just gone over. For ROC, all methods are relatively unbiased in median estimation. Split sampling has the largest spread in the variance. All others are nearly indistinguishable, or I would argue marginally different, not meaningfully different. In terms of mean bias, k-folds are slightly less biased than others. For precision recall, among the k-fold methods, high values of k seem to be more positively biased. It was slight, but it was there. It was observable empirically. K-fold methods in Monte Carlo cross-validation have similarly spread in variance, so that's good to see. And out-of-bag variance is a little larger, is a little bit larger than k-fold, and we're going to investigate this next. So what I mean by that is if we go up here to precision recall, if you looked at the out-of-bag IQR, it's a little bit larger, and so we'll investigate. That has to do with again imbalance in the outcome class. And lastly, Breyer scores. All methods are positively biased and underestimate calibration. Tenfolds less biased than fivefold, and Monte Carlo cross-validation split sampling are the most biased with respect to calibration. So a lot of these results, some of these results at least, can be recognized when we consider class imbalance. As I said, in random forest, we assess the effect of this for these random forest models specifically. So the way I did that was I had 10 data sets with class imbalance less than 30%. So now I'm going to summarize these results that I just went over, but only within these 10 data sets that had less than 30%. And we'll see with AUC, very little changes. These results are largely the same if you compare this to the figure several slides back with all of the data sets. So I'm not going to spend much time on this slide, but with precision recall, note the spread of the IQR and the 95% coverage for out-of-bag estimates. So what we're seeing here is these precision recall estimates are worse than a single split sample, which is pretty bad. And we consider the fact that random forests, and I'll have this on a summary slide coming up, but random forests are just go to it, minimizing out-of-bag error. And I'm sure we can all conceptually understand that if you have a rare outcome and particularly small data, you can minimize that out-of-bag error by just putting everybody in a single class, regardless of any prediction, because that's going to maximize class accuracy, even if it's not useful. And the math is the way the math is. So we'll see with precision recall with imbalanced data, if you're using out-of-bag errors to make your estimates, will you be careful about that? So going back to the early intro slides, you'll see papers saying that for out of bag estimates are perfectly fine to use if your classifier is a random forest. Well, if we only consider AUC, sure, maybe, but we often care more than just what the ROC AUC is. Precision recall means something, especially in medical data. We care a lot about positive predictive values relative to sensitivity because we start thinking about costs and the costs associated with kind of wasting resources on patients who didn't need it. So if you care more than just about ROC AUC, then maybe you shouldn't be relying just on out of bag estimates with random forest classifiers if your data are imbalanced. With calibration, we don't see anything really different. K-fold is better than the split sampling methods. Tenfold's better than fivefold a little bit. Not by much. I mean, it's pretty unbiased there, but nothing substantially different from the entire data set summary. So the results summary of this, results are largely the same for ROC, AUC, and Breyer scores, but the variability of the bias and the out-of-bag estimates are larger than K-folds in Monte Carlo cross-validation and split sampling in the case of imbalanced data sets. And this is largely because of the way random forests work to minimize the out-of-bag error and the effect that rare outcomes has on how that operates. So then I want to look at, well, data sets individually. So here are distributions of the estimates across the 50 repeated samples for each data set. Now, each data set is organized on the y-axis, in this case by N to P ratio. So if you counted these up, there's 47 different sideways box plots here. And we can look at, and I've color coded it by the true median ROC AUC. So what you'll see is the darker the box, the worse performing the model is on the global sample. So it's like, I mean, the really dark blue is pretty much close to, you really don't have a useful model. The really light blues are pretty useful. But we really see, I organize this by N to P, and I don't see any obvious trend. I don't see any obvious association or with N to P. For fivefold cross-validation here between ROC on the left side and PR precision recall on the right. Same thing for imbalance. If I sort the data sets and look at their distributions, again, each distribution is across the 50 repeated samples of that individual data set, and then the boxes are representing the distribution of those 50 repeated samples for that data set. I don't see any obvious trend or association by imbalance when it comes to estimating precision recall or ROC AUC in this case. But now this probably is obvious, but I'm going to point it out anyway. As the true accuracy in the global sample improves, well, the variability around those estimates all improved. The variability around the bias improved, and the bias itself improved. So if you look on the left side and the right side, you'll see like at the bottom where the true models are actually not that good in practice when applied to the global sample. Like you see very large spread ranging basically plus or minus 20% around estimated AUC. It's kind of what we expect. They're not good models, so the estimates of the variance are really large, and then it gets better as the true performance increases. And we see similarly for precision recall, but what we also see with precision recall is that towards those worst performing models there at the bottom, the estimates are actually positively biased. So if you don't have if you have a model that's true accuracy is probably in that 0.5 to 0.7 range, what we're seeing is, generally speaking, with at least with fivefold cross-validation, is your estimated precision recall AUC is going to be a little positively biased. So there's more likely you're going to be positively biased with your precision recall AUC estimates if your true model is not that great. Now, in practice, we don't know if our true model is that great, but again, interesting findings nonetheless. But wait, there's more. If you grew up in the 90s like I did, then you've seen this guy a million times on TV. I'm a statistician at heart, and I have a bunch of data that were generated from this benchmarking study. So I analyzed them statistically. Like I said, I'm a classically trained statistician, so that got into prediction modeling at the start of my career as a faculty role. But I still need to evaluate these statistically. So I can treat bias as an outcome in a mixed model. So first, I'm going to model bias by the method of cross-validation and the subset sample size is 100, 300, or 500, treated as a factor, treated as a categorical variable here. And in this model, I can control for random effects of the data set and the replication of that data set. And then I can summarize the standard deviation of bias across replications within a data set. And then I can run a model and model, well, the effect of cross-validation method and the subsample size on, well, the variance around that bias or standard deviation of that bias. So I can demonstrate these results in an interaction term through these predicted plots from these fitted models. So like I said, I'm a statistician, so I'm going to do that. And here are the results for ROC and PR, ROC AUC and PR AUC. And what we see shouldn't be surprising in terms of sample size. The bigger your sample size gets, the less biased your results are. Well, that's intuitive. We all expect that. But really, the point of this is to show that the methods of cross-validation for k-fold and tenfold are not drastically different from each other as they approach zero, as they approach no bias. But with precision recall AUC, we see actually, we see that five-fold cross-validation is nearly unbiased with 300 and 500 subsamples and close to it with 100, and it's better than tenfold. So this is just, statistically from a linear model showing what we inferred from all of those plots I've showed before. Whereas the methods of split sampling and out-of-bag error estimates are all performing a little bit worse than k-fold cross-validations. But for every method, as your sample size increases, then your estimates get less biased. For Breyer scores, we see zeros down there at the bottom. So anything kind of higher up in this plot is going to be worse performing and kind of pessimistic because these are positive biases and Breyer scores we want low. You'll see tenfold cross-validation metrics, very little difference here between tenfold and 10 times tenfold. Fivefold's a little bit worse, but not drastically. And out-of-bag error estimates are doing pretty good here with Breyer scores. So the calibration's not bad, but methods of cross-validation or Monte Carlo cross-validation and split sampling are a bit worse. And, you look at these plots, you look at the axis, 0.0025 versus 0.005. These aren't massively different means, but the point of this is like, what if we can choose which to use, and they're all computationally about the same, pick the one that's best empirically. Now we look at linear mixed models of the standard deviation of that bias, as I demonstrated in that first slide introducing this concept. And what we see that, well, the spread of the variance is about the same for every single method except for split sampling, which has higher standard deviation around your estimates. But regarding the spread of everything else, they're all the same. And similar with Breyer, there's not much difference there. So considering all of these results, k-fold appears to offer the most robust method of cross-validation in terms of mean, median, and variance of bias in ROC AUC, PR AUC, and Breyer scores. Split sampling is definitely the worst approach in terms of variance and bias. And I'd also reiterate that out-of-bag error estimates are reasonably good when the data outcome class is relatively balanced, but when the outcome class became more unbalanced, less than 30%, 20%, then you really started to suffer in terms of your precision recall estimates. And then, as obviously the biggest obvious statement is, as sample size increases, the mean bias and variance bias decrease. Yes.
Nate, a very quick question. The
Sure.
standard deviation is positive. Did you use a linear mixed model for it with normal errors?
Yes, I did. So good point. So yeah, theoretically, I could have estimated these standard deviations to be negative. I did not get that far into it. I can do some sensitivity analysis before I publish this to assess the effects of that, and I could take the log and make that better. All right, so one more thing. I just deduced here from everything I've just presented that I think K is best. What should K be? again, more conflicting information you can go find on Google Scholar. For the last 20 years, you'll find hundreds of papers assessing k-fold cross-validation, and many come to different conclusions of what k should be. So I repeated these simulations or this benchmarking study for k equals 2 to 99 for each cross-validation method across each data set, across 50 replications, when the subsamples were 100. And I chose 100 so that 99 could represent leave one out. And it would take my computer forever to do this if I had inset to 300 or 500. So I chose the smallest. And we look at, well, the effects of k on ROC AUC estimation. And what we'll see with this plot is representative of what the literature will tell you when it comes to bias variance trade-off aspect. What we see is that the mean bias, the red dots, become less biased as k increases. That's consistent with what you can find. You'll see that the variance also actually goes up a bit, very marginally if you're looking at the IQRs, but it does go up in terms of the IQRs in a 95% spread. So this plot is showing what the literature will tell you, that there is a bias variance trade-off. And as the k increases, you decrease the bias and you decrease the mean bias, but you increase the variance of that estimated bias. So this is consistent. We do see the median bias actually go up as you get close to leave one out cross-validation, actually go a little bit positive. Mean stays unbiased. So this is nothing new. Everybody focuses on this. Most of the papers focus on this. I couldn't find a single paper that was discussing the effect of k on precision recall, so I plotted that. And what we see is high values of k are quite positively biased, up to 5% if up to leave one out, and 75-fold based off a sample of 100. And that just decreases. And until about mean, but it doesn't get, the red dot isn't overlapping the line representing 0 until you hit 7-fold. So mean bias is not, practically 0 until you hit 7-fold cross-validation. But then as you go below 4, it gets actually negatively biased. So there's an interesting sweet spot when it comes to precision recall. And the bias of it when choosing your choice of k. Now, this is for 100-fold cross-validation. This is for a sample size of 100 using leave one out cross-validation. How this would be proportional to, say, leave one out cross-validation if I had a sample of 300 or 500, I don't have that. I'm going to have that, but I've only looked at this for 100 so far. But nevertheless, the point is that higher values of k, while less biased in terms of mean ROC AUC, become positively biased for precision recall AUC. So something to think about. And lastly, with Breyer scores, you're getting negatively biased. So overly optimistic calibration metrics with higher values of k, which, as you can see as k falls, get closer to unbiased until you reach about 15-fold, and then they become positively biased. So there's a sweet spot. If calibration is all that you care about, there's a sweet spot for k. So taking these three things into account, it's not obvious. We shouldn't just only be focusing as researchers and prediction modelists on ROC AUC when we're thinking about cross-validation. There's more metrics that we care about and should consider. And the choice of k isn't as simple as a lot of recommendations and abstracts make it seem to be. So results for optimal choice. To summarize, and I don't have any more things, so this is my last one more thing. I don't have anything else. So to summarize this, ROC AUC, low values of k show some slight negative bias and slightly higher variance. High values of k show slight positive bias and slightly higher variance. And middle values of k in that 5 to 30 range are optimal. This consistent with the variance bias trade-off that we understand to theoretically be true. A precision recall AUC, high values of k are positively biased with higher variance, and as k decreases, bias and variance decrease, and the optimal k appears to be in that 5 to 10 range. And lastly, with Breyer scores, high values of k are negatively biased, which are overly optimistic in terms of the Breyer score. Values of k in the 10 to 20 range appear to be least biased, And then as K continues to decrease from 10 to 2, the positive bias grows, growing your calibration metric estimation to be a little bit overly pessimistic. So overall conclusions of this entire talk, K-fold cross-validation appears to offer the best balance in terms of all of these metrics I've discussed, which is good because I think K-fold is probably most prevalent. I haven't conducted a meta-analysis on every paper in the literature to show that, but anecdotally, being familiar with reading papers, I think K-fold's probably the most used. So, okay, most people are using the right method. Single split samples are clearly the worst performing approach. So you clearly shouldn't be using those with small data. And unfortunately, I do still see that happening. So hopefully people stop. Repeated split sampling or Monte Carlo is reasonably good, but has slightly worse bias than K-fold. And in a world where they're both computationally the same and computation time, why would you choose one that's inferior? Out of estimates for random forest are reasonably good, particularly when the data outcome class is relatively balanced. And the optimal K and K-fold appears to be, I would argue, I say 5 to 10 here, but I've reconsidered that, like 5 to 15, depending on how you want to balance precision recall, ROC, calibration, as this seems to offer the best balance in terms of the overall 3 metrics. So that's a long, 50 something slide presentation of a lot of, I think, are interesting results to kind of come to the conclusion that I think a lot of the literature has kind of adopted 5 and 10-fold cross-validation as the default method, and that's good. It seems to be optimal based on everything I've shown, but now I have empirical results aggregated across close to 50 data sets to back that up. So where am I going from here? Well, I can continue to add more data sets, large open source data sets, or, I'm trying to get all the ones that I can. Assessing performance of these approaches and other classifiers, neural nets, oblique random forest, which will handle more dense data, lower into p ratios better. SVMs, XGBoost, all the classifiers we could use, and continuing to make sure that these results hold for each of these. And then also there's been some more recent work in this area. There's a paper on arXiv right now that kind of assesses the use of smoke versus rows versus up and down sampling with random forests. But also how does your method of handling outcome imbalance in combination with some form of cross-validation affect the overall results? And if accounting for outcome imbalance and using one of these methods to accommodate that would impact the results we saw in precision recall AUC, specifically when it comes to estimate your performance metrics for your random forest fitted model. So I'm acknowledging Jamie Spicer, who is a colleague here at Wake Forest that has collaborated with this work, and a summer intern of mine is a master's student at VCU last summer, who I worked with to get a lot of this programming done. So big thanks to Jerry, because he did a great job. Here's a few references. This is not all encompassing of everything that went through my brain when coming up with this presentation and coming up with this work, but just a few. And I'm now happy to, oh, boom, look at that, 56 minutes. I'm happy now to take and answer questions. I'm happy to receive feedback. And again, thanks all for attending the talk today.